Here we go.
Very good. So we're very excited to have with us today Andreou of Johns Hopkins University. And I very much know Andreas. In fact, let me put it this way. So Andreas actually got me to Hopkins. He was the one who brought me from Caltech when I was a grad student there, and he brought me there. And it has been one of the most exciting times that I had in doing really hands-on neuromorphic design. In fact, also he got me into biomedical circuits too, so it's been very exciting. So let me say a bit more about Andreas. Andreas is really a leading figure in neuromorphic engineering, has been there from the very beginning. In fact, some of the people that came from his lab are like Kobena Bohannan, Philippe Poliquin, right? Then we had many people, right? So that really have driven the field of neuromorphic engineering. So he also spent some time at Caltech. Also, we met there as well, while Carver was starting all this field of neuromorphic engineering. Yeah, so I was very excited to being with Andreas for about 11 years. I was there at Johns Hopkins. We had some good time together with many great things.
Including Grossberg. Remember the time of Grossberg?
Oh yeah, we had all this NURI, this project with building all these chips that implement what was it, the contour, the boundary contour system, and different art systems. It was very much fun. Yeah.
Okay, enough.
Okay, Andreas, go for it.
Okay, hi. What you see here behind me is Cabo Acama in the island of Cyprus. I did my sabbatical there, and I got stuck during COVID. And last year when I came back, I kept putting it as a background to show it's a national park, and it's really a very pretty place at the end of the island. So let me begin and say that's why I also have my affiliation, University of Cyprus, because I do have an adjunct appointment. And let me proceed. This is our team circa 2017. You're gonna see this picture 3 or 4 times. So a few people have graduated, a few people are here, and the team has a few additional members, but we don't have a more recent picture due to COVID. So this is probably for now as good as it has been. We do have a website. We do have a Twitter account that I post things. So if you want to find out what we're doing and whatnot, papers and recent work, please go there. This is really where this is a fun talk. And so let me. This is the outline of the talk. I'll give you a little bit of a history. I'll take you through an architecture that we worked for many years. Then the brainwave architecture is a foundational approach to really try to build silicon brains. And there was 2 projects, the Nano Abacus project, and then the C-Think chipset, which is a more recent one. And that's the one that I think up to that point, I think everything is okay to distribute. The C-Think project involves Northrop Grumman, and even though we are really the people that are driving it, and it was an independent research project, there may be some things there that they would feel a little bit funny about. But anyway, we don't need to ask permission from them. So the early 90s. So I came to Hopkins as a professor, 87, and at that time, there was a lot of excitement about about brains and analog VLSI. And at that point, we didn't have, of course, Siri. Novak Rachel came and interviewed me, and she made a nice article about what we were doing at that time. And just to remind you, at that time, our computers, we had a handful of computers. We had the most powerful computers that we have. It was a Pentium Pro 0.5 micron technology with 5 million transistors, 150 megahertz at 3.3 volts. And then Philippe, one of the key people in the lab, had a DEC Alpha 2164, again, half a micron design, and 200 megahertz, and 65 megabytes of RAM. my God, we had a lot of RAM. And because to do VLSI design, you needed to have RAM and you needed to have disk space. And this is the time where we're writing zip files, and it would take about, I don't know, overnight to write a zip file, a small design. And at that time, we had the CAD environment, which is Magic, RSIM, and SPICE. And this is kind of the same environment that you find today in the open source CAD tools. So this is Deja Vu. We've been doing some open source design recently. Is Deja Vu to Magic and RSIM and SPICE. So in this article, there was a little blip about the silicon retina. This is really the work that we did with Kwabena, who at that time was an undergraduate student, a BS, MS student at Hopkins, and we started this work. And so this is really the current mode retina. Of course, in subsequent designs, we don't have the resistors, we have transistors that basically the various structures in the design encode the physiology of the retina. You have the cones, which are the receptors, photoreceptors that encode color vision and acute vision. And then you have the next cell down the architecture, the retina architecture is the horizontal cells, or the next layer of cells out, because the retina is upside down, as you probably know. And then the horizontal cells and the receptors are connected through gap junctions or electrical junctions. And this is really a model for what you see here. It's a model for the turtle retina. And then there is an excitatory synapse from the photoreceptor to the horizontal cells, and an inhibitory synapse from the horizontal cells back to the photoreceptor. As the animal matures, some of the gap junctions among the cones disappear, they go away. So there is an evolutionary benefit for actually coupling the cones at birth. And if you look at the papers that Kwabena and I wrote, and he wrote with his students subsequently, you're going to see actually how the addition of the gap junctions at the cone network regularizes, in some ways, the data or the input signal, smooths the input signal, and this whole architecture, the combination of the gap junctions in the cones and the horizontal cells, in conjunction with the inhibitory excitatory synapses between the cones and the horizontal cells, yield this essentially a fourth order partial differential equation in space, which is really is known as the thin plate interpolation, that describes the bending of thin plates, and it implements a second order regularizer for the data that comes in the photoreceptors. It is my viewpoint actually that much like you have to regularize your data because there is variability in the data, you also have to regularize, so to speak, quote unquote, the hardware. And so that, I think the coupling there helps you address some of the variability that you may have in the hardware and improves the stability of the system as the system matures and learns how to compensate for that and adapts and whatnot. Anyway, so at that point, we had some collaborators at the applied physics lab and say, okay, this is exciting. And the person that was really spearheading our collaboration is Kim Strobin, who passed away, unfortunately, but Kim, also Gerd knows Kim. And there was a project at that point. This is Kim on the right side here. This is the Flare Genesis project. And the idea is to fly, this project is to fly a balloon-borne observatory around the Antarctica. And this is a completely autonomous operation because you have a low bit rate link a few hundred kilobits per second when you have a line of sight and when weather permits that. And this balloon had a 3-stage system of sun orientation and tracking. So the idea behind this project is you send this above the Antarctica, is moving around because of circumpolar winds around Antarctica. You collect data for 1, 2, 3 weeks, and then you release you send a command, you release the payload, the observatory comes down on in the ice, you go and you collect the data from a tape recorder and you analyze it. So this system used, when they designed the system and they did some ground-based observations, they realized that they really had to do a very good tracking and motion compensation of the platform. Remember, you're flying by yourself, you go up there, and there was a program that basically found the sun, it found sunspots on the sun, and then it focuses on one sunspot, and then activate the retinomorphic tracking system to keep the telescope looking at that particular sunspot. You're going to see some data in the next slide, and working out, collecting data. So this is really the architecture of the system from the paper. It was published in 1992, 93. And you can see on the diagram of the architecture, of the telescope architecture, that was something which is called a silicon retina. That's basically the architecture that Guabena and I worked out, the current mode retina, to do actually contrast enhancement and then subsequently do tracking. Well, the telescope actually flew, and at some point, this is the actual trajectory over the Antarctica. It tracked, it collected data. You're going to see some of the data in the next slide. And at some point at the end here, they had to send the command to go down because it was getting away from land and it was going to land in the ocean and they're going to lose everything. So at some point, they stopped the mission only after one revolution around the Antarctica. The idea was to go multiple times, but the winds shifted and they did that. So this is really some of the early work, and you can go, there is a website and you can look at it. But let's talk a little bit about what did we have? What kind of neuromorphic technology did we have on this balloon? Well, on the left side here, you can see a GIF animation of a solar flare. This is really through the high resolution CCD telescope. And on the right side, somewhere in this background, you see these little granules. And so what the retina, the silicon retina did, it took this low background, this low contrast background around the sunspot, and did contrast enhancement, and then track those granules to keep the telescope looking at that. This is real data from a subsequent mission in 2000. So when the instrument was designed, basically, they really realized that without this compensation, they couldn't really collect good data, because they had the gondola on the ground and they're doing experiments, and they realized that it really is not going to work. So we push ahead and we designed this chip that you see here, and it is a retina chip. It's called RVC. At that point, we call it RVC. This is the chip actually that went on the balloon and helped it stabilize the image. And it used a Ricard, excuse me, a Ricard motion detection, which you may or may not know. In a Ricard motion detection is a correlation-based detection where you will take the contrast and will sum the positive motion. You multiply two neighboring pixels, one going left and the other going right, and then you sum the results, and that's how the Ricard motion detector is inspired by the retina in the fly out of Reichardt and Poggio and Hasselstein, who wrote the original paper. Out of those people, and the Poggio is the one that is at MIT when he did his work, when he did his doctorate research in the Max Planck Institute in Germany. He worked with Reichardt and Hasselstein. So there is a slightly, if you're really familiar with the Hasselstein model of motion computation, you'll be saying, well, there's something here called absolute difference. And in the Reichardt motion detector is a product. Well, it turns out, instead of doing an autocorrelation, we actually do what we call the absolute magnitude difference function, which is equivalent to autocorrelation if you know that your data are normalized and you don't have to divide. You don't need to do the division because you have normalized data. Of course, we have the retina here, and it's much easier to do the absolute value, absolute difference here. We use current mode circuits. So there is some mathematics and some work that describes what we do in this paper. But the nice thing is actually, we got this to work, and this is real data from showing the stabilization of the gondola. And we show that here, experimental data in these two panels over an hour for the azimuth and the elevation tracking. And at that point, you could track with better than 8 arc seconds in elevation and 16 arc seconds in azimuth. And at that time, no other balloon-borne telescope had achieved such sustained precision pointing. Essentially, the pointing precision and motion compensation was as good as the variability in the mechanical structure that actually rotated the gondola. So this is success. This is exciting. I never put together the story. This is the first time I actually tell the story like this, but I think this was really a great example of taking neuromorphic technology and making something useful, really useful out of it, that exploit at that time, the available technology. So any questions so far? I mean, because I'm gonna shift gear to something completely different now. Any thoughts, ideas, questions? Okay, so fast forward now to 2000X, whatever it is today. Oops. Of course, today we live in this third wave of AI, and where we have the environments, and we do sensing, where we turn the signals into the world into signals. We have the process of perception, where signals turn into information. We have an AI machine or a machine intelligence, where we have knowledge and we abstract knowledge, and we use that knowledge to reason about the world. And then we have action, and then we behave, where we turn our behavior back to the world. And this is kind of this is really kind of the big picture about where AI and machine vision is going today. And if you've been to Telluride, this is the kind of things that we do when we get together. We've been doing for the last 25 years when we get together, or at least the last 15 years, when we get together at Telluride, talking about cognitive systems and behavior, and how do we really turn these abstract concepts into real devices. So at some point, it became clear, at least to me, when I started this trip into this 3D silicon brains, that if you compare the brain and modern computers, they both exist in a 3-dimensional physical space, but can deal with problems in hyperdimensional spaces. And I think that's a challenge. you don't just solve, for example, scientific problems such as field problems, which are nearest neighbor problems. You can compute the electric field up and down and left and right, like the connection machine, but both the brains and modern machines really need to deal with hyperdimensional spaces. So that's really the challenge. And the only brain that I know that is really flat is basically Flat Stanley. This is from Jeff Brown, and it's really one of these toy, it's a meme before we had memes about this kid which really exists in a flat space. Now, real brains really deal with this. How do they deal with this challenge of working with hyperdimensional spaces while only having a limited extent in 3 dimensions? Well, if we look at the surface of V1, we see that multiple stimulus modalities are really mapped in a 2D plus delta patches on the surface of the cortex. And this is really the key. And so, however, if we want to do that, we have conflicting constraints. So one constraint, what we want to do is want to maximize coverage. So we want every location in the physical space to be mapped in all possible combination of stimulus modality. At the same time, from a physics and physical perspective, we want to minimize wiring length and metabolic cost, energy. So it makes sense for neurons with similar stimulus response to be in close proximity on the cortical surface. And then hence, you do have smoothness on mapping, like we did have in the retina and the retinomorphic representation, which is easy to do because a retinomorphic representation is simply a 2D projection of a 3D world into a 2D surface. Now, this idea is not new. This idea was put forward by Hubel and Wiesel, where they made this ice cube model of stimulus representation in V1, and where, for example, in this case, orientation and ocular dominance, they are orthogonal and occupy different delta surfaces. So it is imperative that we have this surface be mapped in a 3D space. Of course, you're going to have adaptation. You're going to have the development where you're going to develop or adapt to really move, develop the columnar representation that we see. But this is really the challenge. The challenge is really mapping these hyperdimensional problems into 2D representation. So at some point, we start thinking about if we are going to build machines, brains, what are the abstractions? What kind of work should we be doing at different levels of abstractions to really make efficient machines? And with Andrew Cassidy, who was the chief architect for True North at IBM, he's the first author on a 50-author paper when they presented actually the chip, the real chip. And Julius, which is University of Cyprus, and myself, we really kind of put together this diagram. And basically, essentially, in my mind, still today, the challenge is to do parallel processing, because to do serial processing is very easy. But if you want to compute in parallel, you have a challenge that you have physical constraints, which are wiring, delays, energy, and variability in the representations. So that is really what the brain is trying to solve. So this is really at the foundational level. And then we can look at also at this is really using Mars 3 levels of abstraction. So at the computational level, this is really what we're trying to do. at the algorithmic and architecture representation, we want to map brain architectonics into a chip multiprocessors. We have attractor dynamics and spike-based processing, and we want to map that into fine-grained parallelism and event-based processing that exploits stochasticity. And at the physical level, we want to really abstract from the canonical 3D and columnar organization of brains into modern technologies in 3D. And you see also there emerging technologies, which are flash, 3D CMOS, and also crossbar arrays using memristors that Gerd and you guys and colleagues at UCSD and Stanford presented, did some very nice work in recent years. So this is really the framework that we're working on. And I will just dive in first to the 3D story because it's really a funny story. I'm tenured, I'm full professor. I'm full professor since 1997. But in retrospect, I say, oh my God, how did I make it? Given what you're gonna see next, you know, as a young faculty at Hopkins, we get tenured at full professor level. We used to, not at the associate professor. Now they change it, but I happen to be one of these people. So crazy, totally crazy. So, any questions so far? Well, you're either bored or it's things that you've seen before. So let's move on. So 3D integration. This is really a 20-year saga and the exciting finale. So why 3D? Why 3D? Because, and we wrote this paper in 2006 with Miriam, and then subsequently you can find this graph in the paper that I wrote with Andrew. Essentially, you can find out how much energy you use by just simply plotting the distance that the bits move as you go from the distance between the source and the drain of a transistor to the network. And so you can see you start at something about 10 to the minus 18 joules, and that would be attojoules for a single transistor. And you move on to something like 10 to the minus, what is that, 9 a nanojoule, if you're actually going to go into SerDes and optical communications and whatnot at the network level. And what you see in these blue bars is that you have transistors, you have functional units, you have intra-chip, you have interchip, your network, and every time you move into a different scale of distance, you actually go up in scale in energy, how much the bit costs. This is the cost of a bit. So if you look at this diagram, between the time that you go from a functional unit to the time that you go to the board level, which is interchip, there's basically roughly 2.5 or 3 orders of magnitude of energy change. So if instead of going horizontally on the board level, if you actually could go upwards and downwards to another chip, then you save a lot of energy. And you can see somewhere here, I have the 3D through silicon via, which is now is D. And you can see by going up or down through a 3D silicon via, and I also have the soy via, which is C. It's a little bit less because you have less capacitance, silicon or insulator choice. So you really save a lot of, you save 2.5 orders of magnitude of energy going from this red circle at C and D to I, which is really what it takes to send a bit across a 1 centimeter die. So this is very simple math, very simple based on the capacitances. The numbers actually are a little bit more for the functional blocks. incorporate other costs such as interface costs, the SerDes, the optical transmitter receiver, and whatnot. So this is really an argument why 3D makes sense. And this is an argument why brains actually make sense to be in 3D. We don't have many brains which are actually two-dimensional. So Tesseract technology is a technology that actually allowed to do this. Tesseract semiconductor, they're out of business now. Crossbar ReRAM is also technologies that allow 3D. Simple FinFET embedded DRAM is also 3D. Because if you think about it, embedded DRAM, you have either the crown or the DRAM made in the substrate, and those are all 3D structures. So 3D makes sense, and of course, the ever-spin embedded MRAM also is a 3D structure where you have processing. You can have processing near memory, and they are very close to each other. So technology is moving towards 3D, and it makes a lot of sense. So, however, this is really 20 years ago. One of the, at least in the United States, the effort to advance 3D technology started when Koyanagi and my friend Kurino did some work at Tohoku University in Japan, where they stacked wafers by gluing wafers on top of each other. This is really, I spent 5 months at Tohoku University, and you can see they were using an adhesive layer between wafers, and they were using metal wiring, and they had a very sophisticated contraption apparatus in the lab where they would vacuum the apparatus, and they would let the glue go between the wafers, because otherwise you have bubbles. And so they wrote this paper in 2001 where they made a neuromorphic vision chip. I think this is really the first 3D neuromorphic chip. So Kurino came and spent a year at Hopkins, and these diagrams are courtesy of him. And I went and I spent 5 months at the Tohoku University, and I was convinced that this is really the way to do it. Of course, not, I mean, going beyond this. Koyanagi actually is the inventor of the crown DRAM cell. If you're in the technology, there is 2 DRAM approaches. One builds the cell in a 3D structure on top of the transistor. The other builds, and that is the Hitachi and the Japanese approach. And the other, the IBM approach, builds the DRAM embedded in the substrate in a deep trench. That's how you get the capacitance. So obviously, Koyanagi had some sense of what's important, and that's really why this early work happened in 3D. Now, sure enough, the US government got excited about that, and they got MIT Lincoln Lab to design a 3D process, an experimental 3D process. This is based on a SOI technology, which you see here, 0.18 micron SOI, 1 poly 3 metal with mid capacitors, and the thickness of the CMOS layers were 18 micron, and they did the vias through the substrate because SOI substrate. And this is our first multi-project chip. We are very ambitious. We had a silicon retina. We have a silicon cortex on this chip. We had all kinds of other amplifiers, bioamplifiers, MEMS pixels, you name it. And it was a 3D CMOS process. We must have spent like 2006. Now I know why I did this, because at that time I was tenure. I'm sorry. If I wasn't tenure, I probably would not be doing things like this. So this is the technology. We got the first chip. We got something to work. The second chip, they was supposed to be run in 2007. We improved the design. We refabbed the chips. nothing worked because Lincoln, after waiting for a year and a half, they forgotten to do a processing step in the fabrication. So they say, okay, we'll have a third run. And now we're really, remember, we started this something like 2005. The MIT third multi-project run was run in 2009. We designed all kinds of different cells now. We are really convinced this is going to work. We even have asynchronous event-based transceiver interfaces. We had neural arrays. We had the alpha neurons on this chip. This is really what this is all about. And so we fabbed and nothing worked. So, but we wrote a lot of papers. Don't bother to read this. This is not meant to for you to read. This slide is meant to show you that in the period of, I don't know, 3 or 4 years, 5 years, we wrote a lot of papers about things that were encouraging results. And if you're building chips, everybody knows when you're saying the results are encouraging, it means that you really didn't get anything to work. So you got something to work, you maybe got a transistor to work, maybe you get a transfer function, maybe we had, in this case, we have all kinds of things that kind of showed evidence of life, but nothing for real. So that is my second phase of 3D design. So any questions? So still,
Andreas, to give credit, it's not that nothing. I mean, you have plenty of chips that work, right? I mean, so yes.
I know, but for about 7 years, we had nothing working. I mean, really, we had transistors, we had little circuits, nothing for real.
And so anyway, it's because the models are off? The models are off?
No,
the process.
I'm glad that you asked this question. The problem with that is that Lincoln Labs was doing the fabrication, and they couldn't get their fab to do the right integration, to do the right steps. So it's like going to Stanford and Stanford don't having their act together and screwing up, and you don't get your chips that you guys got. I mean, I shouldn't really, maybe we shouldn't put it on post this talk.
So how was your experience with Tezeron, Andreas? Was it better?
Okay, well, it's coming next.
Oh, okay, good, very good. Good.
I mean, I wouldn't, there is an inside joke here. We used to have a jury with some colleagues from Boston University, and Gerd was at the acoustic jury, remember, Gerd? Yes. And every year we have a meeting, and our colleagues from Boston, they will show like a list of chips that never worked.
You mean Alan Hubbard? Yes, I know.
Yes, remember that?
No, our chips work though. We had our boundary control system.
Our chips work, but I mean, for 2 years in a row, 3 years in a row, you come year after year and year, we try this, didn't work, we try this, didn't work. Anyway, no, there is some good stuff coming up. So, Tezeron. So Tezeron basically was a small startup by a fellow named Bob Patty. And they started really, DARPA decided they're gonna go to a company and they're gonna get the company to really do a run and build 3D chips with TSVs. At that point, IBM was reporting about 170,000 TSVs per millimeter square, which means actually this technology was viable. And they made some DRAMs and they demonstrated some DRAM chips with this technology. So things look good for a while. So 2009, DARPA multi-project run tape out. The memory, the 3D memory for this multi-project was supposed to make by Samsung, by a small company that Tezeron fabricated the DRAM. But 2010, Samsung sued the small company and they shut it down. So the small company couldn't make in Japan the company couldn't make the chips. No, we shouldn't really publish this. This is really, this is really literally a talk.
Right, Andreas, in fact, we were in the same run. We had this stack of our higher alpha chip. It will be totally integrating higher hierarchical additive routing and alpha integrated fire rate receivers. And we were never able to get the higher part because the DRAM connection was not there.
Yes, and it never came back. Okay, so the summer 2012, we did manage to get some logic wafers chips back. And in 2013, that is 4 years later from the original tape out, the DRAM wafers came back. And the November of that year, both now the 3D DRAM and the 3D CMOS chips came back. They did came back. But as Gerd pointed, and we have a pretty picture. That's a pretty picture of our DRAM, of our chips sitting on top of a DRAM stack. It's a real picture from that we took here. Well, again, this sounds terrible, but on that run, we had two designs. One is and this is really quite exciting. One was a design of a silicon retina that implemented both rods and cones in a single pixel. And you're gonna see some data. We never published this, but this is the only so far, I don't know of anybody else that built a chip like this, of a silicon retina that can change mode by switching a bias on the device. So we can take the detector and make it a single photon avalanche photodetector by increasing the bias on this bias wire here, or we can lower it down at 2.5 volts or 3 volts, and then the device is operating like an APS or more like a time of flight active pixel sensor, where you start counting, you create TDA, where you count how long you integrate for that period, and you get the intensity. Now, here is, okay, we got 8 chips back. We blew 6 of those chips. The other chip, we didn't blow it. I don't think it worked. But this is really data from one of those chips. On the left side, you can see the silicon retina operating in the lab with the light. You can see the light reflection in the eye of the little doll there. And basically, you illuminate the little doll, and then you get that picture. Then you turn all the lights off in the lab. And the only lights that you have on is basically the light of an oscilloscope that we had, and the oscilloscope screen was off too. But the pilot line, the oscilloscope was on because it was collecting data. And you have a little pilot line. So that was the only light in the lab. And what you can see on the right side, you can see the same image, but now this image is really is integrating single photons at every pixel. So we have now actually a silicon retina that both operates in the single photon regime, Geiger counting mode, and at the same time, it can be turned back to really operate in an APS or in a traditional integrated mode. And this is exciting.
You mentioned this is room temperature, right?
This is room temperature, yes.
Yes.
And you can see it's a little bit different. You can see there's a wall on the left and there is a wall on the right. The wall on the right is a little bit warmer than the wall on the right, because what this retina is measuring is actually a little bit short infrared. It's not measuring visible, but it's measuring essentially some reflection, but also it is operating in kind of pseudo-infrared regime. So you're seeing something that you see from an infrared, a combination of a visible camera and an infrared camera. And on this little corner on the right side, if you're concerned what is this is, and on the top side on the right corner, what you see, if I had a video of this, you're gonna see waves coming through. Basically, it's called after pulsing. The retina the Retina Basic Apps Plus. Anyway, I will proceed because I want to finish at least this part. So this was exciting. We got 3D, and then also we got another 3D. There's a little paper on this, I believe. It's a scalable and programmable simplicial CNN digital pixel processor architecture with Petro Julian. We got this to work. It basically was a 2-tier processor architecture with a cell array on the first tier, and it had an 8051 microcontroller on the second tier, and there was communication between the tiers. And you can see here we are doing morphological processing, which is median filtering, dilation. This is really classical block recognition, all on the chip, without going between the layers on the chip. This is really cool. It worked. And this is, we are writing functions who can program the chip, and it will do this 3D, this processing on the die, between the two dies. What you see before is real data from the chip. So we have success. So this is our team now, 2017. Sorry. This is, I don't know why my, oops. Sorry, just a second, close. This is, I'm gonna stop here for a second and kill, oops. Okay, there you go. Let me kill my, why did I have my email running? I should have killed it. Let me kill it so it doesn't come up. Okay, let's continue. So the team, we're doing good. Let's move on. We're gonna do more things. And I have only about 10 minutes. No, how much time? About 10 minutes? Yeah. I actually started about 5 minutes later. So we're gonna build now a new architecture, a neuromorphic architecture using computing by counting. And we call it the nano abacus because if you think about it, everything that the brain is doing involves unary representation in space and in time. So you really count in space and you count in time. And that's the only things you have. Those are your abstractions. So we wanted to do this. We got funded. The early work on Abacus is a Salamis tablet in Greece. The Swapan was a Chinese origin Abacus, and then Soroban was a Japanese version of an abacus, and then the Upana is an abacus used to do arithmetic by counting back in the day of Incas. So this is really, I mean, counting using an abacus-like architecture, it was something that it's been done forever, and unary representations. So we wanted to compute, to design an architecture to solve vision and machine intelligence problems at that point, including Bayesian inference. We're building the Bayesian probabilistic computing systems. And we basically rely on computation, local computation, where we store the charge in arrays and we add. This is work that charge-based computation is something that Gert did early when he was here at Hopkins, and it's amazing, very efficient. I'm surprised why we didn't pursue it, more people pursue it, but I think this is really the way to do very efficient systems. Then we use stochastic representation to do scalar multiplication, and we use encoding and decoding. We build complete systems. We do the accuracy of the computations can be configured before runtime by setting the number of events we want to spiking events we want to add. That defines the precision. We have digital hardware designed to operate at 400 millivolts. We have analog hardware operating at 500 millivolts. We built 3 or 4 generations of test chips. Everything worked, including a change point detection algorithm implemented on a chip doing exact Bayesian inference by computing not with probability density functions, but by using actually probabilities. And long story, but this is the kind of things we think the brain must be doing if it's computing things in a stochastic way. It cannot be building PDFs, and it cannot be computing function approximations and deep neural networks at the elementary level. It must be doing something more basic, and so counting is the way to do it. We use cadence. We designed this in 55. We had flash ESF3 cells that we got licensed for this project, and we're going to use 3D and 2.5D chiplets. Chiplets are very modular. You have an interposer, you design modular components, and then you put it on the chiplet. Computing environment now is a recent Threadripper, 120 years later, with 500 gigabytes of RAM and a terabyte of solid state drive. We have Synopsys and Mentor graphics, which are still not good for this. And here is the chip we're going to build. The chip is a silicon interposer. You're going to see a real picture of this. That had 3 chiplets, neuromorphic chiplets, and a Xilinx Zing FPGA for operating system support, and a 3D RAM in a shared memory multiprocessor. So this is a shared memory multiprocessor. The DRAM has basically a NOC on the DRAM, and you could have 4,000 wires, and you could access up to 4 gigabyte that memory in 32-bit chunks. So we have an amazing technology. We built bits and pieces, and we built the interposer. What you are seeing here is a silicon interposer, not the cadence on the bottom and the real wafer on the top, fabricated. It basically uses 4 radicals stitched together, 5 metal layers, about 8,000 standard C4 pads on chiplets. We actually make this. This was fabricated, and the interposer was tested. And then DARPA basically came and said, this is a DARPA project, you need to finish the project now. We won't give you extension to really complete it. We scrambled to design the project. This is the memory. We built every chiplet had an M0. It had 2 processors, an M0 and a more beefy one for memory for NOC management. We had a very high-speed data bus. We had 2 NOCs, a token ring NOC and a mesh fabric, much like your chips that you guys built. We built the chips. We had 4 different designs for different chiplets, each one doing different things. You can, Gerd will recognize the one on the left is a CID structure. This is where we started doing the CID DRAM mixed signal computation. We fabricated this thing. I'm going to skip this slide about what this thing is doing. And here is the result. The chips came back, and this is the team. And basically, May 20, 2017, we got the chips back, and we realized because of some cadence problem, we could not handle such large designs, mixed signal design. There was a left problem, a long story, so we got a wafer back, but the chips did not work. And we couldn't get anything to work because we couldn't boot the processors to actually test the chips. My God, what a disaster, $1.5 million disaster. At that point, the project finished, and we see, well, we came back to Northrop Grumman, and Northrop Grumman, the good folks of Northrop Grumman says, okay, why don't we give you some money to really redesign these chips? We did. This is really where the good news happened now. We modify slightly the design. They help us. We have better tools. We taped this out in November 2020, and we got the chips to work. This is the Think chip. which involves 49 processors. This has not been published. We're testing the chips now. Basically, these processors do hyperdimensional computing. A lot of you guys there are working. We have a Silicon 521 and a Silicon 5 RISC-V S7 processor. We have caches, and this is how the cores look. We have 49 cores. This is data from the cores, and we characterize all the units, so the units work. We have variability. Oops. Okay. Yes, I will answer your question about the 62 millivolts. I just saw your email. Okay, your text. So we show here with this chip running a benchmark, an HD benchmark. We compute at about performance at about 10 to 100 times better than an FPGA, and much better than, these are real chips. The chip is running. This is really, Jamal did it about a month ago or 2 months ago. And so, of course, we have the C chip, and the C chip looks exactly the same, but instead of processors now, we have pixels there. So we have the pixels, everything else is the same. It's a modular design. So we have a 64 by 64 multimodal pixel array and 64 sigma delta pixels for ultra wide dynamic range. This is the chip. It looks like this. We integrated backside illuminated silicon photodiodes, and what you can see here, and I have a video which I will skip, but we have now basically, we can read out from this architecture the pixels. You're gonna tell me now, it looks like there's space between the compute units. How do you really compress that space to really make a uniform mosaic of detectors? Well, we use wiring, and we found out the wiring to come down to this like roughly 1 millimeter by 1 millimeter super metapixels, so that the mosaic is uniform, but the underlying structure is that looks something like a chip multiprocessor. And of course, this is 3D. You can see the chip and data. And now everybody is happy again. And you can see smiles in everybody's face. So this is really where we are right now. And we have more exciting testing, doing testing and chip design and other project that we have now. But before finishing up, and give me 1 more minute, I want to really finish by giving an ode to 2 friends and collaborators. Hiro Kurino, remember from the best guys that did 3D VLSI from Tohoku University, passed very young, something like 35 years old. And he died basically out of overworking. He was working too hard and basically got sick and basically died and passed. And then Kim Stroben, collaborator from the Flare Genesis project, someone that really turned a lot of the analog neuromorphic chips that we built into real useful devices for various people and agencies. Also passed 3 years ago out of cancer. I would just say it's unfortunate and sad that they are not with us to witness how much progress we have made. And this talk is really dedicated to these 2 people. Okay, I'm done. I hope this was at least a semi-entertaining talk and not too much technical details, but if someone wants to ask questions, I'm happy to do that. And but you see how the field is and what we did wrong and what we did right, and failures and why. I have to say that the failure getting a $1.5 million wafer run, dedicated wafer run for our group and not working. You don't know how much disappointed I was on that day, but it was, yes. So to answer your question, someone asked a question, when a limit of 400 is mentioned for digital is a minimum energy point for that particular process. Actually, what we did there, the minimum energy point is the minimum voltage is something like 45 millivolts and demonstrated by Lotz and Manolis. And there's a little story there, but I don't have time to say it here, to tell the story there. However, at 45 millivolts, you are not at the minimum energy point. At 45 millivolts, because your cells are basically Schmidt trigger, you're burning power, leakage current in your Schmidt trigger. That's how you operate at 45 millivolts. You don't have inverters, you have Schmidt triggers. And the extra transistors actually burn you power. We spent a lot of time trying to do that, and it didn't work. And we ended up actually designing our own library in 55 nanometers, which we have, that actually a cell library that we use to compile all the digital circuits that only has 3 transistors in the series. We basically took out all the transistors, and we had a few cells that we needed to design, including some asynchronous cells. And we create our own library that allow us to compile now complex logic using only cells that involve 3 stacked transistors, so you can go down to 400. Did I answer your question? A lot of technical stuff here that I skipped over. But
by the way, Snorra is joining us all the way from Norway, I believe so, right? So it's great to have people joining all over the world.
Yeah, that's great. I mean, shoot me an email. I mean, Gert and I, we are really, we should really collaborate more, Gert. I think, and we're trying to do that. And
we are, right? We're part of this FENS DARPA program. It's great.
We're going to do other proposals, but I think it's exciting. I think this is really, but as you saw, it took, at some point, you need really to press hard to take the silicon retina that started with Quabena and Meissler and Andreas, and make it into a real instrument. And then people were convinced they couldn't live without it. They could not do that mission, because once they see how good they could stabilize the telescope, they said, how else are we going to do this? This is not going to work.
Yes.
Anyway, that's really okay. And I'm sorry for the neuroscientists. I could talk more about some of the ideas, how I think in this probabilistic processor that we built to do Bayesian inference, we discovered circuits that look like bursty cells, and we need them to actually normalize the computations. So, we're doing design, and all of a sudden we're finding out, but we need the cell to actually fire. To fire 5 spikes, every spike you get input, because that's how we actually normalize the result. So those kind of bursty cells that you see in biology, and so it kind of feeding back to this idea of maybe you can come back from biology to biology and say, well, you have this because this is really maybe this is what this is doing.
Hi, Andreas. Question for you.
Yeah.
What are you going to build? What are you going to build next? Yeah.
Huh?
What are you going to build next?
Well, ask Gert. Gert knows exactly the 2 things that we're trying to do next.
Okay.
Did I say it, right? You can say it.
Sum it up.
Well, we have an exciting project. Gert is part of it, where we are building a 3D Sirius 4 megapixel silicon retina, an event camera, and that's the first layer. And then in 130, we can talk about that. Yeah, I guess we can, but please don't pause. Maybe I can edit the video if you want me to, put on Facebook. And then behind that, there is a processor to do basically computation, a stack processor underneath using 65 nanometer. And Gert is doing all kinds of designs there to minimize the power and do using adiabatic logic and all kinds of really exciting things. And then we're going to bid for another project. We're working on another project to do basically to solve problems that are really optimization problems. And even if we don't send it to DARPA yet, we can send it to NSF. I think we can get funding from NSF on a small project. So we should really write a proposal.
Yeah.
Okay, thank you.
And also that involves chiplets. The idea is to build a platform where you deal with high speed I/O, and also we're going to use your facility to do simulations of this neuromorphic
Yes. Yeah.
We're using the UCSD computational infrastructure to simulate things at that scale. But the idea is to build a chiplet that provides a platform for I/O, and then on the chiplet we can build analog chiplets that have different functionalities to really do different things.
Okay.
Anyway, thank you guys for listening. And if you visit, you want to visit, or maybe I'll come and visit Gerd one of these days. Maybe I'm looking for an excuse to get out of town and meet you informally, and we can have a real chalk talk where I can go on the board and talk about details.
And the nature here is very much like Cyprus. I think you will like it here, Andreas.
Yes, I know. I would. Okay, thank you all, and thank you.
And
a plug for Telluride. We're working to have an in-person Telluride this year. We should really plan maybe a working group. We're just talking about announcing it, but it would be fun to really, yeah.
It'll be hybrid, right? We'll have a hybrid in the mountains and also
yes,
still.
And it will be in person. We're trying to do it in person.
Yeah.
And hybrid. This could be hybrid, but there will be about 40 people, 50 people at Telluride, if you want to come. Okay. See you guys.
Thank you.
Thank you, Andreas.
Bye-bye.
Bye-bye.